Good morning. I'm John Yebrook with NASA's Office of Communications. We're here today at Vandenberg Air Force Base in California to preview the launch of the Orbiting Carbon Observatory-2, which is slated to launch tomorrow at 2:56 a.m. Pacific Time here at Vandenberg. This event is a NASA social, which is NASA taking that online experience of people following us on social media, on the web, offline, to give you a behind-the-scenes access of our missions of exploration and discovery. This is our 81st NASA social we've done as an agency. We started back in January 2009 doing these, and they've been tremendously successful. If you're interested in ever being part of a NASA social, you can follow us on @NASA or go to the web at nasa.gov/social. Today, we'll be taking questions here at the audience, folks from social media, but also from those at home that want to ask questions. The hashtag is #AskNASA. If you want to follow us on the web, on Twitter, the account is @NASA, and I am OCO-2. OCO-2 is going to provide space-based observations of atmospheric carbon dioxide. And here with us to tell us a little bit more about that and give you a big picture overview of the Earth Science Division at NASA is Ken Jux, who is the program scientist at NASA headquarters. Let me introduce Ken to you. Thank you.
Thank you, and good morning. It's truly an honor for me to be here to talk with you. I happen to be the program scientist for the original OCO, so I'm really excited to be here today. So I want to ask you all, raise your hand if you have never taken an Earth Science course in your life. There's a few hands up. Notice my hand's up. I'm an Earth scientist, and I never took an Earth Science course in my life. But I did study chemistry and physics back when I was in graduate school, so that was kind of the basis for it. I remember one day in graduate school, we had a group meeting, and my thesis advisor came up and talked about the ozone hole. And he was showing all these theories about what people thought was going on. It was before we really understood. And I was seeing all these chemistry equations and how all these things interconnected, and I said, man, that is really complicated. Well, turns out the entire Earth science system is even more complicated. And if you guys can pull up the first graphic that I have, I'll try to explain that to you some. Actually, it's the graphic, different graphic than that one. It's the one on the Earth science system. You can go back one. But what happens with the Earth science system? We have a coupling. We've got the sun, we've got the Earth's atmosphere, we've got the Earth's surface, we have the Earth's ocean, and all of these things interconnect in ways that it's really clear. Here's the graphic right here. So you can see we have all these cycles that go on where the sun provides the heat to the Earth's atmosphere. It heats the atmosphere, it heats the surface, it heats the ocean, and the Earth is trying to get rid of all of that heat as well. And also we have things like trees and we have agriculture. All of those things are exchanging with the Earth's atmosphere. They're all putting things into the ocean's circulating, it's exchanging all these things around. So in order to really understand the system, you need a lot of data, and you need a lot of different types of data. And just an example of how we do some of these things, let's go to the next one, and I'll bring you back to the ozone hole. Because it turns out when I left graduate school, I got a job where I started to study ozone. I was doing observations from NASA aircraft and from high-altitude balloons, which is kind of a poor man's satellite. And we were trying to study and understand the processes that affected the ozone layer. So you can see these are images that we got from a NASA satellite called TOMS. Over the years, it was one of the first things that told us about what the ozone hole was, how it developed. But the satellite data alone wasn't enough. So in order to really understand those questions, what NASA did is we put together an aircraft campaign. And we have a graphic here showing some of our NASA Earth Science airborne observations have get going. And that's actually how I cut my teeth. The very first thing I did when I left graduate school was to go on that plane right there you see flying. And it was an experience that was like no other. I was hooked. I wasn't sure whether I wanted to stay in Earth science. After I did that campaign, I was an Earth scientist. I stuck at it. And we were doing measurements over the North Pole all the time. We were trying to understand why there wasn't an ozone hole over the North Pole at that time. And there was a big volcano that occurred around that time. And it put up a lot of aerosols way up in the stratosphere. And the satellite we had up at that time was saying, ooh, something strange is going on over the equator. So we got to go fly over the equator, landed in Tahiti, a really tough place to go spend a day, and go back. But doing all of that work helped me to fully realize that we need a lot of data in order to fully understand what's going on in the Earth system. Actually, you can see all these people working on here. I actually know some of these people. So I got to spend a couple hundred hours flying around the world doing things very much like that. It was a lot of fun. But eventually I started working more and more with NASA and started to understand all of the satellite data that we have. And I was first playing with just data from a few satellites, and then over time became a few more and a few more. NASA has a lot of satellites up right now, and they're designed primarily to try to understand this big, complicated Earth system. And if you could show this next graphic, it actually shows you all of the satellites that NASA has up orbiting the Earth right now. And we're going to put one more up there in the morning, and we're very excited about that. So you can see all of those going on, and each one of those satellites has anywhere from 1 to 5 instruments on board, and some of those instruments measure many parameters at a time. Some measure just one. All of them are critical. All of them are important. What we don't have up right now in NASA's system is a satellite that measures CO2 near the surface, which is something that we really need to understand. And fortunately for you all, you're going to have one of my colleagues here at the end, Anne-Marie Eldering, is going to tell you a lot of the critical elements of what they're going to do with the OCO data. I'll leave that to her. But by combining all of these data, if we can go back to that original slide that I had, just to show you at least what some of these satellites are actually doing. So if you look in there, we show you the carbon cycle. We have the trees and the forest. We have satellites that actually image that surface all the time. And when you see things in a newspaper about things going on, you see these NASA images, it's probably from that one particular instrument that's on one of the satellites called MODIS, which is a very important instrument. We have a number of instruments that look at the Earth's atmosphere. That's primarily what I used to do. There's the ORIS satellite, which is up right now, which looks a lot at the entire atmosphere system. I'm actually the program scientist for that one as well, so I'm very excited about the people who I know in the ORIS science community who want to use OCO data. So I hope I gave you a good idea as the big picture of what we try to do in Earth science and the types of hard questions we try to go after. So I'll stop right there and take questions from you all.
Any questions?
Yes.
Hold on, please wait for the mic. Hold on a second.
Okay.
You showed us that graphic of all the satellites that are going around the Earth right now that NASA has up. How many are there up there right now?
We have 17 up right now,
Okay.
soon to be 18.
Thanks.
And for those at home, if you have any questions, you can use the hashtag on social media, AskNASA. Ken would be happy to answer those for you as well. Any other questions in the room?
Okay.
1 second.
Hi, Christina Walsh with OFA. I'm very interested in how long before you'll be able to collect data. You have to catch this A train
Yeah,
and
that's
practice
correct.
steering or something? And
Yes, that's right. We're going to put this satellite at the very front. When you saw that graphic of the orbiting satellites, you saw a bunch of them that were right together. It's going to go on the front end of that. And it's going to take anywhere from a few weeks to a month or so to get to that right spot. The less time, the better, because we're all eager to get the data. And then after that, we're going to have to cool down the instrument, cool down the detectors, make sure everything's working okay. It's going to take us 2 or 3 months in order to really have the data and start streaming it out for scientists around the world to actually start using. And my colleague Randy, who's going to come up shortly, a couple speakers from now, he's the real instrument geek behind this instrument. So he's going to tell you a lot of fun stuff about that as well. Okay. Like that, Randy? I called you a geek. I'm sure you're happy.
Question I have, the data that you get, is it going to be coupled with any other NASA data or other space agency data?
Always. All of NASA's data we posted on these data portals, which are called DACs. Don't ask me what DAC stands for. It's an acronym. We're at NASA. We like lots of our acronyms. But these data are free and open for everybody to use. And the data from all the other satellites are on these same DACs as well, and they interconnect. And we also, on these DACs, we connect to data from space agencies in Europe and Japan. So we share a lot of our data around because, like I said earlier, to fully understand your system, you need a lot of data. So taking advantage of all the data that's out there is the only way to really go after the questions that we're trying to answer. Okay, yes?
Hi, Matt Campbell at CBS LA. Can you touch really briefly on what it's like when you have the data compiled, other organizations such as NOAA or EPA, what's the communication like with that data?
Well, the communications are on a lot of levels. From scientist to scientist, we call each other up. But people will download the data, but to truly understand how to use the data, sometimes you need to talk to the people who produce it, because that really helps you to make sure you're using the data in the right way. There are operational agencies who like to take data and put it into their models for forecasts and things like that. And they work out systems with our data portals to directly downlink the data. So you just call them up, we work out a mechanism so they can get the data fast, and they plug it straight into their models. And that's how it works.
Thank you.
Any other questions?
Got one more here.
Yeah, Ken, what's the timeline for the public dissemination of the research results whenever this guy comes out? I'm from the Lunar Lion team, and we are totally interested in everything that has to do with the OCO-2 results.
So when the data will be out probably by the end of the year, and then it's going to take the scientists some time to start truly understanding the data. So I would anticipate a lot of the initial results. People are going to be looking at the easier questions you can answer over the shorter period of time. And some of those papers could be submitted to journals in a matter of months after the data are out. Some of the analyses are going to take years worth of data in order to truly put them into their models in order to try to answer different types of science questions. So I would suspect that we're going to be getting papers from OCO-2 data coming out over the next decade or two.
Great. And where can we find these papers when they come out?
They'll be in all sorts of scientific journals, so everywhere. And ones that people feel are really important, there's usually a press release that goes out with them as well.
Awesome.
So,
thank you.
Yeah.
Okay. For those in the room, if you could leave your hand up until we find you, it'd be great.
Okay. Yes.
Another question for you. Do you all have a hypothesis as to what's currently going on and how it might be fixed or how we can improve the situation?
Scientists always have hypotheses. That's what we do. We ask questions and we take the data and hope that the data will help to answer the question. They usually answer it at about the 70% level, sometimes the 90% level. It's rarely the 100% level. There are hypotheses right now about how CO2 is being taken out of the atmosphere. There's a lot of natural processes that go on. Quantifying what the major drivers are is a real problem right now, and we hope that because of the coverage that OCO-2 is going to get around the globe and the breadth of the data and the precision of the data, that we'll be able to take what people are currently trying to answer those questions at kind of like the 30 and 40% level and raise that up. So that's the type of thing we want to do. But scientists we're greedy, we like data, there's never enough. You always need more data to answer that next question.
Hi, my name is Derek Letelier. My question for you is, what's the next step after OCO-2? What would you like to see? Maybe some other kind of measurements, maybe, I don't know, methane. Is there anything else you would like to see after the end of the program or the next step?
NASA has a lot of missions in the queue right now. So we have a soil moisture mission coming up later this year. There's a couple missions that will go up onto the International Space Station soon. NASA recently, through a competitively selected process, have an air quality mission that will be launching in about 4 years. That's going to go onto a commercial communication satellite from geostationary orbit. It's the first time NASA's tried to do something like that. And that's going to stare at North America and look at pollution events. So for things like methane, there's actually a mission that our colleagues in Europe are launching very soon, which is going to have a channel to measure methane as well. So a lot of scientists are anticipating combining that the methane data from the European instrument with the OCO-2 data, because I think combining those two data sets could answer a lot of very important questions.
Excellent. Thank you.
Okay. Okay. Yes.
Hi, Ryan Malati, earth2ryan.com. I guess I kind of have a two-part question.
Okay.
So as we all know, the first OCO mission failed in 2009, and that was about 5 years ago.
Right.
So I wanted to know if the technology or the mission has progressed or changed in any way since the 5 years has passed. And also, do you find it a happy coincidence that CO2 is now in the name of the second satellite?
Well, the name of the satellite was by design. the OCO, the Orbiting Carbon Observatory, is oxygen, carbon, oxygen. So that was by design. That was a nice punny thing, but the people who came up with the original name. This particular instrument is very similar to the original. There are a few minor tweaks to it. We learned some things when we did the first one, when we went through testing and the pre-launch stuff, that we said, you know, if we're going to do this better, a few small changes here and there are going to make this better. And Randy, who you're going to hear about from later, he was kind of the brains behind doing all these small tweaks. But then there's just some other small changes because computers were obsolete, so we had to replace some things like that.
Was it kind of a blessing in disguise then that you're having more advanced equipment up there?
We wanted the data then, and we want the data now. Having a launch failure is never a blessing. So,
thank you.
Okay.
Hi. How long do you expect the OCO-2 probe to function?
It's designed to last for 2 years in orbit. With all of our missions, there's usually a design lifetime, and if at the end of that time the mission is still producing good scientific data, we keep it up. So most of those orbiting satellites you saw there are all well past their design lifetime. I mentioned the Aura satellite. It was designed for 5 years. Later this month, I get to go up and celebrate the 10-year anniversary of Aura being at launch, so I'm very excited about that as well. And we hope that we could have OCO up for that long as well. It's possible that it could if we're lucky and parts don't break. Yes.
Hi, good morning. I actually work in high schools, and so you were talking about the fact that the data will start to be available towards the end of 2014.
Yes.
Is there any plan to put together curricular components that teachers could be able to use in their schools for things like the carbon footprint question?
NASA does have education programs that do disseminate data out for teachers in the communities and things like that. I would recommend that you interact with them and they can work with a scientist to help try to get data like that out for teachers such as yourself who are interested in that.
Thank you.
Okay, I think we have time for one more question. I think we have some on social media. Veronica?
All right, we have a lot of questions coming in over Twitter, and for those of you on Twitter, if we can't ask them all out loud, we will just try to respond to you through Twitter, but I'll ask you, let's see, Dr. Heidi Maston asked, at what point did you get really excited when you realized solutions to the big questions of carbon data were within your reach?
People are always excited when they hear the mission is coming that's going to get the data, so that's kind of where the excitement comes from. So when the original OCO mission was selected, it was through a competitively selected process. All the people in those communities who had been thinking about that and trying to help the people who wrote the proposal come up with a measurement design system that could actually answer the questions. As soon as they get a yes on that, that's when the excitement starts. And the same thing happened with OCO-2 when we got allowance from the U.S. federal government to actually refly this mission. Again, that excitement comes back.
Another one here is from Ag Hub. Will the data gathered from the OCO-2 satellite help farmers in any way?
Ooh. In some ways it could, in some ways it couldn't. So the measurements aren't going to map over farms per se. That's too fine of a scale for something like CO2 that has a very long lifetime. However, what it can tell us is the amount of exchange of CO2 over larger scale. So if you have an area that's either getting a lot of rainfall or going through serious drought, we should be able to get some type of picture as to how much carbon dioxide is exchanging with that type of area. You're going to hear from Anne-Marie a little bit later about one of the side benefit measurements we're going to get from OCO-2, and there's a measurement called solar-induced fluorescence. And what that measurement tells you is how active photosynthesis is. That's going to be a side measurement we're going to get out of OCO-2. And in some of these certain types of environments where you either have drought or a lot of rain, we'll be able to tell how active the photosynthesis is in those particular areas, which does directly relate to agriculture.
Thanks. Thanks, Ken. I think that's all the time we've got. I really appreciate you coming out today.
Oh, great. It was a pleasure.
A round of hand for Ken. Thank you. For those in the room, if you have a question, please raise your hand and hold it up, and we'll try to get to you as quickly as possible. For those at home, you can use the hashtag #AskNASA. We'll try to get to your question as soon as possible. If we can't get it to you here in the room, we'll try to answer it for you on Twitter or on other social media accounts that you ask it on. Our next speakers are going to talk a little bit about the launch itself, the vehicle, what the conditions are for launch tomorrow. Let me introduce Colonel Keith Baltz with the 30th Space Wing Commander and Launch Decision Authority, and Mick Waltman with the Launch Services Program, the Vehicle Systems Engineer. Thank you.
Well, good morning. How's everybody doing? Good? How many of you is this your first trip to Vandenberg Air Force Base? All right, well, let me be, as a base commander, let me welcome you to Vandenberg Air Force Base. I know you just got started here this morning with the social kickoff. You're going to get a chance to see a Space Launch Complex, or SLIC, later this morning, SLIC-2. Cacheo Park, so we're excited. We love this base. Third largest Air Force base in the inventory. It's spread out 100,000 acres because our job is to launch rockets and to test missiles. And so tonight we get to launch a rocket. And so we're pretty happy. We haven't launched a Delta-2 since October of 2011, so it's been a few years for this particular rocket. We just had a very successful Missile Defense Agency intercept test last week, if you saw that in the news. That was launched from one of our launch facilities on the north part of base. And so here we are a week later, now getting to work with another fantastic mission partner in NASA, and they're a partner with JPL and the satellite to put that on orbit tonight. So before I get into my job, not just as a base commander, but later on as the Launch Decision Authority for tonight's launch as the owner of the range, I want to hand it over to Mick Waltman. We'll talk a little bit more about the launch flow as the rocket and the payload come here on Vandenberg. Over to you, Mick.
Thanks, Colonel Baltz. On top of that, I'll ask, how many of you, this is your first time seeing a Delta-2? All right, that's great, because I can tell you from Launch Services Program, which we're from Kennedy Space Center, we're very excited to be back in the Delta-2 business. As Colonel Baltz said, it's been about 3 years since our last launch NPP, and OCO-2 is a very special vehicle to us due to the reflight and all. But on top of that also, I'm going to just start off with saying you'll notice when you do your tour today, you'll see a special placard out on the fixed umbilical tower. That's a special for us is one of our analysts, Lori Walls, recently passed away, and we've dedicated this flight to Lori. So I send that out to Lori and her family, and we're looking for a great launch this evening. So with that, enjoy the launch this evening. A little bit about Launch Services Program. As I said, we're from Kennedy Space Center in Florida. We do launch here on the West Coast at Vandenberg Air Force Base and at Kennedy Space Center. Very happy to be with the Delta-2. As we move forward, our engineers are analysts. We bring a great, vast knowledge of Delta-2 forward on this vehicle and are ready to go. I'm going to show you a little video here of the launch flow. It's about a minute long. Talk that real quick. If I can get the video. There it is. If you look at this, you'll see the first stage booster coming into SLIC-2, Space Launch Complex 2, as we're getting ready to erect it into the mobile service tower there, being lifted up by the mobile crane. There's a great picture of the RS-27 main engine for the Delta-2. It's about 237,000 pounds of thrust for that, and the vehicle going into the mobile tower. Here's a very early morning getting ready to erect the second stage, which is powered by an Aerojet Rocketdyne AJ-10 engine, which is about 9,300 pounds of thrust. Again, lifting the second stage up into the mobile tower and coming back down, mating it onto the first stage, which has already had the solid rocket motors placed. Great view of OCO-2 in the payload processing facility, getting ready for transport. We're putting a can on top of OCO-2 to protect it. It's more for clean environment and shock as it transports down the road. The payload processing facility is only about 2 miles from SLIC-2. Here you see it coming into SLIC-2 in the can. We get ready to lift it up into the clean room on SLIC-2. That's a very slow and methodical process there. As the ULA NASA team brings the can down in, they made it on top of the second stage, and then we get ready to remove the can and close up the clean room. So the OCO-2 vehicle is now mated to the launch vehicle. We bring in the 10-foot composite fairings there. You see the one half already on. It's made by ATK and IUCA. And we bring in the second half of the 10-foot composite fairing do an inspection of the separation seam there, make sure everything's ready to go. And now we have a fully encapsulated OCO-2 on top of the launch vehicle in the clean room there. That's a really nice view of the top of the rocket. I think that's it. Yeah, from the launch vehicle processing standpoint. I will say the team's been really busy. We did range beacon checks yesterday. We finished up our launch readiness review with the base here and with our NASA senior management and ULA senior management, and we're looking really good for this evening and moving forward. So I appreciate that, and back to you.
Thanks, man. Good tag team here. We got a lot of great partners here. Our job here at the 30th Space Wing at Vandenberg is to launch safely, whether we're doing a missile test or, in the case of tonight, put a satellite in orbit. My primary responsibility is public safety. And so we have different launch customers come into the range. My job is to make sure that this, with that kind of explosive power on that rocket, that it doesn't affect our local folks in Santa Maria, Lompoc, the base population, as long as folks up and down the seaboard. So if you ever look at the geography of California and this little elbow of California that sticks out, when we put a polar launch into orbit like we are tonight, we have a lot of things in play that have to come together for launch day. The weather has to be good, and it's looking good tonight. Not so much for visibility, so I apologize for those that may see the fog.
Some of the best weather I've seen in Vandenberg, by the way.
Yeah, it is good. It is good weather. But some fog tonight, so visibility may be low for the actual launch, but as far as meeting our launch commit criteria, the weather's looking good, 0 probability of violation, so that's good news for us. In addition to that, we have to make sure the area is clearance. So there are no people in the launch area. That includes boats, trains, planes, and people on the ground, even though we're near the ocean. So we have sweep teams that are out there making that happen along with surveillance radars. In addition to that, we have safety equipment on these rockets so that when we track it, if it's not going where it should be, we crack it. And so we have telemetry and radars, and if we need to, command transmitters to make sure that if it's going in the wrong direction, which I don't expect it to tonight, we haven't had that occur in several years. We're there to keep the public safe. And ultimately, that's our goal of the range. And we're excited because while we never have to do that part of our mission, we're always ready if we need to. And in the end, we get to watch rocket launches for a living and be a part of great teams to make that happen. I think that's good for opening comments. If you guys are ready, we'll take questions and we'll pass the mic back and forth depending on who you're addressing.
Okay, we have one back here.
Hi, I'm Kat at Kat Robinson. I just had a question about, if you would talk a little bit about the launch window. It's a very narrow time frame, so just talk about, maybe for ULA and choosing launch windows, trajectories, putting it into the right orbit.
So yeah, we have a very short window this evening, 30-second window. That's mainly chosen due to the science opportunity that you heard from previously. So once the science is determined and what orbit we need to put the satellite into, then the analysts and the team get together, our flight design team, they determine trajectory and how long our window can be. And so for this mission, yes, a very short window, but we've had shorter ones on Delta II before, and the team is we're ready to go and meet our opportunity this evening. Actually, the shortest one we've had has been 1 second. That's a mission to Mars.
For Colonel Baltz, I'm Matt Campbell at CBS-LA. For a rocket such as the Delta II, how far away will folks be able to either see or hear the rocket at launch time?
Depends the varying levels. This has 3 solid rocket motors on the side, so that's good. Those are crowd pleasers because solid rockets are reverberate on the chest a lot more than just the just the liquid fueled stage 1. So it varies. We certainly, in our operations centers, which are a good 5 to 10 miles away from the launch site, feel it inside the buildings. Those that are going to be at the golf course, I know tonight, or at the media location, perhaps where you're going to be at, certainly see it. Even if it's foggy, at least the fog will get bright for a few seconds before it shoots away. So you'll see it. They feel it in Lompoc and Santa Maria. A lot of it depends on the rocket size. It's been a while since we've launched a Delta II with 3 solids on, so I don't have a good mile distance, but certainly Santa Maria, 15 miles away, in Lompoc, they'll feel it. May not wake folks up at 3 in the morning. Won't be that quite reverberate that much. But sometimes weather plays too. If we have an inversion layer and it pushes some of that vibration, it'll be felt a lot deeper into the coast or off the coast. But the cities will feel a little bit of it tonight. And certainly if it's clear, you're higher above the fog, you'll see it all the way through stage 1 cutoff and stage 2 ignition, and then it'll probably sneak away into the night.
Thank you. Thanks.
Hi, I'm Clayton Elder from UC Irvine. What advantages does the Delta-2 rocket have over the last rocket that was used for the original OCO-2 launch?
Wow. Well, being a vehicle systems engineer working for LSP, one of the nice things is we do get to work with all the vehicles in our fleet. So advantages or disadvantages, I will say that the one big advantage with the Delta-2 is it has been a real workhorse for NASA over the years. I'm actually going to defer real quick because my numbers man is in the back, our NASA launch manager, Tim Dunn. Tim, this is our 42nd launch from Vandenberg. So it has been a real workhorse for us in Launch Services Program. As you saw in the video, a lot of room in the payload fairing, 10-foot composite fairing with OCO-2 and all. So very proven system, very able to meet our requirements and work. So it's a larger rocket than what was previously used for the OCO-2 or OCO mission, and we're really looking forward to it tonight. It's like I said, our workhorse in our fleet.
Excellent, thank you.
Another question about the 30-second window. Colonel, you said you were the launch decision authority. Does that mean that you literally make the call, or is it a civilian military decision, or is it entirely in your hands to press the button?
No, it's a mutual decision when it comes to the launch decision. If I've got a good range and the public is going to be safe and the weather's good and my systems are working correctly and I'm ready to go, I give the final clear to launch at around L-12. The problem is I'm not going to compel the rocket and the satellite to launch if they're not ready. Conversely, if the rocket and the satellite are ready to go, all the technical things are worked out and their checklists are running smoothly and they're go for launch, they're not going to launch without my clear to launch if the range isn't ready to keep the public safe and to meet our criteria. So there is a series of goes from the Chief of Safety, from our Operations Director on our side. We get one from the NASA Launch Manager and the Launch Director to make sure the launch vehicle and the satellite are ready to go. And so it's a dual vote system, if you will, and one can veto the other. They can't launch without the range being ready, and if my range is ready, I'm not going to compel them to launch if they're not ready, and they both come together. And I do want to do one follow-up on where to see it. I'm not sure about the Delta-2, but I know you've got a lot of folks out on the blogosphere today. They have seen some launches, especially space launches, from as far away as Las Vegas, that far inland. Certainly along the coast on the southerly trajectory down by LA, Santa Barbara, they can see it too if the weather's clear. So it's not just a local Santa Barbara County activity tonight. Do you want to add to it?
Yeah, actually, I was just going to follow up to her question. Being the LDA for the Air Force side, as I mentioned, we have our NASA launch manager back here in the back, Tim Dunn. He's the authority for us on the NASA side. And then standing next to Tim is Mr. Ralph Basilio, who is the launch authority for the spacecraft side. So it takes a really diverse team to bring this all together. And, of course, we won't go if the range isn't go. So.
Mitchell Brockman from Union Grove High School in Wisconsin. Question in regards to the rocket. You said the rocket had been a workhorse for both NASA and used a bunch at the Air Force Base, and that it was kind of getting phased out. What is the next rocket that's on the way, and what would be the reasons for phasing it out if it has been so successful?
Colonel Balt says it's my rocket. Go ahead and answer. So to answer that question, this is Delta 367, so 367 Deltas, Delta 2s that have launched. It has been a real workhorse not only for NASA but also for the Air Force in their GPS constellation. Unfortunately, as things happen in the launch business, suppliers and parts become obsolete and things get shut down, and that's the case with Delta 2. Things are starting to come towards the end of the program. The nice thing for NASA is we do have 4 missions left, counting OCO-2. So for us, our next one is SMAP, and don't ask me the acronym right off the top of my head. Soil, moisture, yeah, somebody said it. There you go. That's November 5th here in Vandenberg also. So that's really the reason the Delta 2 program is starting to fade off, is just attrition and design, how it goes. And ULA has made a business decision to move on to other rockets. So from that case, we'll be looking at some Atlas 5s, some Delta 4s, some other vehicles we have in our fleet for launch services program on how we would meet the needs of our customers for future launches.
Hi. Following on to the question about the launch decision and who actually gets to quote unquote press the button, is there actually a button? Is it red? And can I press it?
So let me answer the second question first. No. There is actually a button. I will say that. There is actually a button. So just briefly giving you the overview of how the last few seconds of the count go, there are several polls going on in the last few minutes of the count to get down to that point where they press the button for launch. Colonel Baltz on his side has a whole team that's working with him that he's polling, and as he said, getting ready for go. Tim Dunn, our NASA launch manager, has a whole team, including his engineering team, his chief engineer, his management, all that he's polling. ULA, the launch director, Don Malin, has a whole ULA engineering team and management team behind him that he is polling. And once all those people feed in, they've reviewed all the data, they've looked at everything, and everything's go for launch, then Colonel Baltz, Tim, and Ralph Basilio, SMD, give a final go to the LD permission to launch, and the LD is the one who gets to, tell us we're going. So it's a really big team effort, and those last few minutes are really exciting for the team because you're finishing up your last preps, looking at all your data, making sure all your systems are ready to support, and it gets really hectic there when you start hearing the go, 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 and that's really exciting time for the launch team all around. Did you want to?
I was just going to add. As we get our polls, as we go through on each side, it is amazing to watch this team. I equate it to an orchestra. I mean, we're all practicing our individual instruments during a given day or a given set of months, or in some cases years, to get to launch day. And to see it all come together, make beautiful music, if you will, and crescendo at the same time is just eye-watering. Not just in our ops centers, but there's other ops centers. I mean, there's young airmen out there on SF, Security Forces patrols, making sure the area is safe. We've got young airmen that are watching the area for planes, trains, and boats, as I like to say. We've got young airmen on console along with our contractor teammates and along with some senior civilians and junior civilian, government civilians that help operate the equipment or at least provide expert engineering advice. And so in the end, the final clear to launch at L-12 minutes comes from the Chief of Safety, my policy on public safety, my operations director who's putting all those instrumentation, making sure that's good, and then the launch director, which is a combined vote from NASA and ULA just prior to that. They all get to say go. I don't get to say go. I get to say clear to launch. So that's my 3 words that sets things in motion for those final minutes as the automated countdown timers and buttons, if you will, start executing at the launch pad. Just for numbers real quick, 42nd Delta II launch from here. I think it's the 51st time NASA's used a Delta II. We have a great partnership. We've launched 117 things, or will tonight, from NASA here on the Western Range, as we like to call it. So this is certainly a partnership that's long-lasting.
Okay, so that was totally the same question I had. But so I guess I might say, no,
the numbers won't change.
Well, I guess what I might ask is, okay, in 1 or 2 words, what's it like when you get to say clear to launch?
Clear to launch. Enormous responsibility. I'll tell you, some launches, like I hope happens tonight, when everything's green and clean through the launch, it's just fun to watch, to be honest with you. I know that there's a lot of hard work that went into it. There's other times that it's been pretty give and take right up to launch time. A 30-second window is not exciting for us, right? That doesn't give us a lot of wiggle room if we have some problems with boats, planes, trains, or instrumentation. It's either going to happen tonight or it's not. Some of our other launches have 6-hour windows starting at 3 a.m. And so while that gives us a lot of margin throughout the night, and we've launched late in that window too, it can make for a long night. But either way, we get down to launch. We've been down to 16 seconds before launch, at least ones that I've been on, and we've had to abort. And because of a window, we're able to do it that night. Other cases, we've had to wait till the next day. I will say about 45 minutes out, we dim the lights in my ops center just to kind of get everybody's head in the game. And then about 1 minute out, you'll see a bunch of us stand up. My job is done a few minutes previous to that when I give the clearance, and then we get to watch it go. We're inside a building, so it's not as much fun to be as it is to be outside. But it's still neat to really see the team come together. Yep, question.
Hi, I'm Lenore Look. I met Jim Norman yesterday, the Director of Launch Services from Washington, D.C., and he told me that it takes 8 minutes to go from 0 to Mach 22. So when does that 30-second window start during those 8 minutes?
So the 8 minutes that Jim talked about is from liftoff, for the time we start the engine until we get to the Mach. All right, so the time actually starts right as when we ignite the RS-27 and the ground lit solids. That's our zero mark, that's T0. So from there to there is that 8 minute time frame. And the 30-second window is a time time that we can get OCO-2 into its proper orbit during the day today. So we have to target our T0 time to be within that 30-second window. Does that make sense? So we have a 30-second window today, and we have to target, as we count down, we have to target our ignition within that 30-second window to be able to hit the spot that we need to put OCO-2 into orbit, taking into account all of our thrust and orbital trajectories and flight design. So the 30-second window doesn't really play into that 8 minutes at all. That 8 minutes is a separate from when we ignite the rocket. She's looking confused still.
Yeah, I'm usually confused.
All right, so at what point is the project team going to start to relax and go, this is working? Or are you going to be on pins and needles all the way out to 2 full hours till the end of the second stage?
So I would say from the project team perspective, I would let them answer that. But from what I know from past missions, and I would say it's no different for OCO-2 today, is the launch team and the project team are going to relax once the solar arrays are deployed, and the satellite is in good health, and they report back that they're charging and getting good signal back. So, and if I recall, that's actually about an hour, right? An hour after liftoff. So we'll still be a little nervous during that time. So.
Rodney Mason, Rod Moose on Twitter. I have 2 questions for you. The first question, how do you choose the location where the launch takes place?
So that is based on the flight design and trajectory that's needed for the satellite. In this case, it's a polar orbit. To get into OCO-2 will be the lead satellite in the A train, or the afternoon train, which is a number of satellites orbiting the Earth for Earth sciences. So to get it into that spot, we actually require a polar orbit to get there. So we choose Vandenberg Air Force Station for that inclination and polar orbit.
Great. Second question.
Yeah, let me just follow up, because I think it's important. You're all familiar with Cape Canaveral, and not to get into physics and orbital dynamics, but when you're trying to put a satellite that goes around the equator, like DirecTV and communication satellites, you want to be close to the equator, and you want to face east to take advantage of the Earth's rotation. Hence Cape Canaveral down in Florida, right? It's pretty far south that we can get in the CONUS in the United States, and then they can face east over that ocean, so they don't put anybody in harm's way. When you want to go in a north-south orbit, meaning around the poles, or as we call polar orbits, you want to launch north and south. And I mentioned this briefly up front. There's not many places, if you look at the geography of the U.S., that you can launch north or south without overflying other land masses, either U.S. property or even our countries to our south or Canada to the north. And so this little elbow of California, why Vandenberg exists and why we'll be here, is that we can launch due south as Santa Barbara and Los Angeles fade away to the east, and do that safely without putting anybody else in harm's way.
Excellent.
That's a physics lesson for the day. That's all you're going to get. So there we go.
Yeah, no, that's an excellent answer, and I never knew that, so I appreciate it. Second question I have, the first OCO launch, there were complications. Can you speak to that just briefly, and what precautions or measures are taking place so that this is a successful launch?
So briefly, I'll just tell you, I think most people know the original OCO launch did not make orbit due to a payload fairing not separating. That's what occurred. Precautions and things that have been taken since then is, of course, we're on a Delta II vehicle, which is a completely different fairing system, completely different SEP system, and everything. So again, as I stated before, Delta II has been a workhorse for us in the launch services program. We're very confident in the Delta II vehicle and all of its systems, and we're very familiar with this vehicle, and we've done a lot of work to get to this point and be ready to go for launch this evening. I will tell you, as Colonel was saying earlier about being on console, the gentleman's question over here, for me this is a special one because I was also the vehicle systems engineer for the prior OCO launch. And so for me, it'll be a little emotional this evening when I give my go to my chief engineer, not only from that aspect, but again, very proud to be back launching Delta IIs here on the West Coast. So tonight might be a little more emotional than an engineer is used to. So.
Great. Thank you both. Excellent answers.
Hi. So, like every other photographer here, my followers are looking for visual impact. And so when I hear about the fog conditions we're anticipating, the first question that comes to mind is, do our weather models give us any insights as far as where the top of the fog layer might be? Are there vantage spots I can choose as a backup to shoot from above the fog, even if further away?
No, that's great. I'd have to go down and chase that information. I know fog layers vary. It's 1 to 2 mile visibility at the surface. There are some places around here though that get you some elevation to see. So picking a spot may be beneficial, but I'm not sure what the cloud tops are. 900 feet. Yeah, 900. Go ahead. You got it.
About not weatherman. About 900 feet is what the Colonel's airman told us at our launch briefing this morning.
All right.
Good,
Thank you.
good.
Second related question, trying to anticipate the angular altitude of the vehicle off the horizon when it sort of fades away. Is it a fist at arm's length? Is it a couple fists? Doesn't have to be precise number of degrees. I'm just trying to anticipate how high up in the sky do I frame a shot.
Yeah, I'm trying to think off of if I were at the golf course parking lot looking at Slick 2, I would have to say, as my NASA launch manager would very much appreciate, probably 3 holes to the right you want to hit your putt. So about 3 cup lengths. So fists probably is where you'll see it.
Unfortunately, we don't have any more time for any additional questions, but if you guys can stick around afterward, I think we have like 30 minutes, so those in the audience who have additional questions, they'd be happy to answer for you, I'm assuming.
We'd love to.
Great. Thank you. Thank you, Colonel. Thank you, Mick. Next, we're going to talk a little bit about the engineering that went behind OCO-2. Let me introduce our next speakers. We have Randy Pollock, who is the project architect with OCO-2, and Pavani Padada, who is the verification and validation lead for OCO-2.
So good morning, everyone. Am I on? Okay. My name is Randy Pollock. I am the project architect is my latest title, but I've been involved in this project for 13 and a half years. Helped write the original proposal, and I think I had the best job on the project. I have worked on the instrument. I work with the science team. I get to lead tests. I've been working operations lately. So I've gotten to do a little bit of everything on this mission and really enjoyed it. My personal milestone, going back 13 and a half years, is when I started on this job, my son was in kindergarten. He's an intern at JPL this summer. So it's been a few years working on this job. A little bit about the instrument. We are measuring 3 absorption lines, 1 of oxygen and 2 of CO2 in the near infrared, so just out past where your eye responds to red light. The instrument, if you look at it, if you were to look at a diagram, and there are plenty of papers out there, you'll see an instrument that wouldn't have been out of place in an optics textbook in the 1800s. It is a very simple instrument in principle, but to make a measurement that's good to a part per million on carbon dioxide, it had to be one of the best instruments like it ever built. We have plenty of things where our tolerances are measured in a few microns. The focus of this instrument has to be known to a couple of microns, a few percent of the thickness of a human hair. And that when we measured it on the ground, we have to be sure that that's going to still be the same when we get up into space. And so Pavani will talk a little bit later about the test program to make sure that that happened. And that then we can trust that when we get up there, it's going to work well. It's the part per million that we're trying to measure carbon dioxide. When it comes down to those engineering requirements, some of them are kind of easy. We only need to know how bright the lights are. If we see a signal, we need to know how bright that signal is to just a couple of percent, which doesn't sound like it's that hard. But for each point on the ground, we measure 3,000 separate colors. And if we make a mistake on one of them, we have to make the same mistake to a fraction of a fraction of a fraction of percent on all of them. So all 3,000 can be wrong, but all 3,000 of them have to be wrong precisely together to a factor of about 4 orders of magnitude. We have to measure the color to under 1 part per million. Know the center wavelength response of each of those 3,000 colors. So it's an instrument that is not so much about the uniqueness and the high technology that so much of what NASA does is about. It's about just doing something unbelievably precisely and accurately. So it's been quite a challenge to get it put together. There were some questions earlier about what we did differently on OCO-2. So OCO, when I started on it, launch was December 2005. And I was so excited about working on a mission that was going to be over quickly. It's going to be great. We're going to get it put together, we're going to get it tested, we're going to get it up there, and we're going to get data. And as often happens on these sorts of programs, NASA called us after we went through about a 1.5-year proposal process where they were reviewing whether they really thought we could do it. And they said, congratulations, you've been selected. Don't quit your day job. We had about a year before we really got money going. And then there were other issues as we went along that stretched the launch out a couple more years until we were all of a sudden in early 2009. And then, as all of you know by now, the rocket did not get us into orbit. And so we spent about another year putting together what it would take to build another one. The original mission we tried to do very cheaply, so we had no spare parts to speak of. So we had to go out and call all the manufacturers, find the ones that were still in business in a few cases, and if they weren't, find somebody else who could build the parts. And so it was a little bit of a challenge. The goal was to not change anything because we were trying to do it quickly. But because the next mission that was on the same rocket OCO was on had the similar failure, NASA made the decision to move us to the Delta-2. What was supposed to be about 2.5 or 3 years has now turned into 5. So it's been a while. A couple of other things. There was a little bit of discussion about early in the mission. I thought I'd add a little more detail. Right after launch, we have about an hour where we're still attached to the rocket. At that point, we'll come off somewhere over the coast of Africa, and a few minutes later, the solar panel should be released, which is a big deal for us. Our battery we're running on battery that first hour, and we need those solar powers out to start collecting charge. But that's just the first step. It's going to take about a week to check out the engineering systems on the spacecraft. We're going into a formation with several other spacecraft, and so until we've shown that the spacecraft works, we're going to launch about 15 kilometers below all of the spacecraft we want to be with. So that first week is checking out the spacecraft works, and then we have to essentially merge with traffic. And you're merging with traffic that's going 17,000 miles an hour. So it takes a little while, and it takes a lot of precision. So that's going to be a few weeks of very gentle nudges with our thrusters to get us up into that position. And then it'll be a couple more weeks of checking out the instrument and starting to see the first science data. So we'll probably be releasing the first images is the wrong word, spectra, the first data, a few weeks out from that as a press conference. So probably September, October will be our first light equivalent. And then over the next several months, there'll be more and more data coming out that shows more and more of the scientific results leading up to what Ken was talking about late this year of getting the first real detailed CO2 measurements out. And with that, I'll hand it off to Pavani.
Good morning. It's nice to see everyone out here. Just a few highlights or key things about, I started this project not 13 years ago, more like 4 years ago, around 2010 of August, and it's been an amazing ride working with some really great engineers and talent. You know, everyone thinks it's easy to build instruments or to, you know, come up with ideas. It's not. It's pretty tough and challenging, and the people who've put in hundreds of hours of work have really given it their all. And besides Randy, I mean, the entire team is looking forward to seeing the success of OCO-2 tonight. So there's a lot of excitement and nervousness right now. Like I said, I've been on OCO-2 for 4 years. I'm the project verification and validation lead. What that means is effectively I have to take a look at all the requirements that are needed to make sure that we have the right instrument, we have the right interfaces to our spacecraft, our launch vehicle, and confirm that we're doing the right thing, we're building the right instrument. We're not just, you know, building something and not know how it interacts or how we actually verify our level 1 science requirement. The final goal is to make sure we can actually produce the science that we've signed up to do. So there's a lot of work that goes into it. That is the testing. We have such a comprehensive testing program that are put together and that are done at various levels. At the component level, a subsystem level, instrument level, spacecraft team has its own set of comprehensive tests that are performed, and then finally the observatory testing, which is when we integrate both the instrument and the spacecraft together. Some of the key testing that you'll see, or I don't know if you've heard of, is thermal vacuum testing. What this is to mimic space environment to see how our instrument performs to the different temperatures, what happens, do we have any failures, do we understand our thermal profile and our system, and how do we deal with it? If we see a problem come up, how do we deal with it? So there's a lot of baselining happening. Second aspect of that is we do two sets of, hello? Sorry. We do two, dead.
We have redundant systems.
Yes, well, on OCO-2, not so much. It's a single string instrument. So one of the key aspects is we do something called a vibe test. And the vibe test is really important. There's two sets. We do one at the instrument level, and then once we're integrated to the spacecraft, we have some test equipment that we're integrated with for the launch vehicle. And this is to mimic launch loads, which is really important. The observatory in its entirety will see the toughest launch loads when we launch tonight. And if it can survive that, it can get through anything. So it's really, really important for a test program to be very comprehensive. And a lot of that is not just testing. We actually have a really good analysis to base this off of. We have to start off with analysis before we can even have predictions saying, okay, these are our predictions, and we map it and we correlate it. So the final report that we receive is not just your analysis and the test data. We have engineers correlating all of this to make sure that it's correct and we're within our margins. If something is off, well, we need to go back and look and see, what's happened. So overall, the OCO-2 program, there's a lot of testing that's happened over the number of years, and it's been refined. Requirements have been looked at more closely, and working with Randy, there's been a lot of back and forth, I think. So. Well, we're looking forward to launching tonight.
Thank you. We now have some time to take some questions. Let's start right here in the back of the room.
Hi. Said before, I'm Kat Robinson, but I also work with the website Geek Girls Night Out. One thing that we love about NASA is women are so well represented here. So I wondered if you would just take a minute and talk a little bit about your journey, how you got into what you're doing, something like that, just because it's very encouraging, for not only someone my age, but for young women to be able to see women doing well in engineering fields.
So it's funny because I was 16 years old. I came to JPL for an open house at that time with a friend or a neighbor, and that's when I knew I was coming back. So I graduated high school. At 19, I got my first internship at JPL, and end of this year, December, it'll be 20 years since I've been there. So for me, I knew I was coming back. There was no doubt about it. I love what I do. There's good days, there's bad days, but it has always been an amazing journey. As a hardware engineer, I love tinkering with stuff. So if there are, kids out there, little girls, boys, it doesn't matter. If you enjoy doing something, go after it. It is so much fun. Space, especially working at JPL for me, it's all about, we're doing unique things, science in a way that we haven't seen before. It's one of a kind. It's not your everyday thing. So I definitely encourage, young people out there to go after it. When you're in college, go after internships. Don't waste your summer. Go get in there, do hands-on stuff. Even if you're in high school, if you can get an opportunity, go in. Trust me, my first interview at JPL was actually in public affairs, and my then supervisor, he couldn't make up his mind. I called him every week, same time, same day, saying, have you made your decision yet? He finally got so fed up, he gave me the job. So that was my introduction into, I knew I was going to stay there for a short time, but from there, I went on to different things, and I knew exactly where I wanted to be by the time I was done. So best part is working flight projects.
Hi, I'm Emily with Mission Control Communications. I'm interested in the solar power system on the satellite. Can you tell me what the similarities and differences are in the solar panel technology versus what would be on the ground on Earth? And then second, are you going to be storing the energy in any kind of battery or storage system?
All right, so the solar arrays on board the spacecraft are a little different than you'd have on your house. First of all, there's no rain, there's no dust, so they're not weatherproof. If you walk up to them, they don't look nearly as rugged as what you would expect to see. You just see these little pieces of crystal glued onto an aluminum, very thin aluminum sheet. These solar arrays are not silicon, they're germanium. They're more efficient, but they're much more expensive. But when it costs so much to put things into space, everything we lightweight. There is a battery on the spacecraft. Our orbit is something called a sun-synchronous orbit. So we always are orbiting the Earth. If we're on the day side of the Earth, it's about 1:30 in the afternoon. If we're on the night side of the Earth, it's about 1:30 in the morning. And we stay in the same geometry with the sun the entire time, and the Earth spins underneath us, so that you'll eventually see the whole planet as it spins, but we always see it at the same time of day, which helps the measurement because the geometry of the sunlight hitting the Earth and going back up to the spacecraft is always the same wherever you are. It's a very popular orbit. The animation that Ken showed earlier with all of the Earth science orbiters, there were 5 or 6 of them that sort of were going together, and that's the formation that we're going into. So with our orbit, you end up with about 60 minutes a day, 65 minutes a day in sunlight, and then we have a battery to carry us through the time we're in shadow of the Earth.
Hi, Liam Nye from the Lunar Lion team at Penn State. We're a Google Lunar X Prize competitor, a bunch of students working on a spacecraft. So we do a lot of this stuff every day, but one of my questions is, what's the most technically worrisome portion of this mission from an engineering perspective? Because that's stuff we think about all the time.
I'll start with the easy answer, all of it.
Okay.
You know, if you're going to be in this job, you're one of those people that says, what can go wrong? And then go, and have a very long thought process to go, okay, what could go wrong? You know, a good engineer is rarely an optimist. You're always thinking about all of the things that could go wrong and how to plan for them, how to make the design robust so that if it happens. You know, at this point, we've gone and tested the hardware over and over and over. We're confident in it. I can't pick any one moment more than any others to say that's a critical event. They're all important. I don't know if you want to add to that.
You know, Randy's absolutely right. It's everything is important, and it may seem, you know, that little aluminum satellite build right there looks, you know, oh, it shouldn't be that complicated. Well, you know, overall design is not complicated, but trust me, making sure that the science we get, it is very complicated. And every single aspect, all the testing that we did is to make sure that we can survive almost anything that can be thrown at us except micrometeoroids. So we don't have control over that.
So actually, while I'm holding the model, I do want to say a couple of things about it. I've heard now for a couple of years since we were picked on the Delta-2 that this was going to be the smallest spacecraft that they've ever launched. This is not quite how small it is. This is a 1/10 scale model. So I've struggled for years on what the size to tell people to get a scale for it was. And for years I would say a phone booth. Other people would say, you know, one of the original scientists on the project would talk about 2 oil barrels stacked on top of each other. And a couple of weeks ago, there was actually a nice event for family members of the people working on the team to come see the spacecraft just before it went to the launch pad. And one of my colleagues' daughters, who's about 10, walked out and was so excited because she convinced me what the phone booth really was. So for those of you out there who are science fiction fans, it's the size of a TARDIS. And unfortunately, as someone who had to shove all of this hardware into this little box, it is not bigger on the inside. So it's a pretty small spacecraft, but we're real excited about it.
Thank you.
Hi again, Mitchell Brockman, Union Grove High School. My question, that's perfect lead-in, is in regards to the satellite itself. I think obviously we all know what the solar panels look like, but I'm looking at the image behind you guys, and I think I see a thruster on there, and it just kind of makes sense to me, like the outside of the satellite would be smooth, but I see a lot of stuff that's kind of like built out of it. Is that because it is so small on the inside?
All right, well, I'll walk you through some of the things on this picture because these are probably easier to work with. First of all, you see the solar panels. For launch right now, they're folded up, and these 4 circles are part of the mechanism to hold the solar panel tight during launch so the vibration doesn't damage these, because they are very flimsy when they come out. You'll also see several of these dark areas on the spacecraft that are a little rough. Those are radiators. So they're designed to get rid of the heat that all of the electronics on board the spacecraft are generating so that we don't overheat. A lot of the other gray material here are thermal blankets to keep the sunshine and the heat from the Earth from coming in. So the ratio of how much is radiator to how much is blanket helps us maintain the temperature at about room temperature. Most of the hardware on this system wants to work about the temperature of this room right now. There are a handful of components that don't. These 2 radiators are specific to the instrument. One of them cools the optics down to probably about 20 degrees Fahrenheit. We are so sensitive that the noise, we have to be able to measure the signal to a few electrons on each pixel on the detector. And to do that, we had to get the glow that just comes from the optics being, if they were at room temperature, it would swamp the measurement we're trying to make. So we had to cool them down a little. The other radiator helps cool our detectors, and our detectors have to run, sorry, I'm used to thinking about this in centigrade, about 150 below 0 centigrade. So quite cold, and again, it's to get the noise down so that there's very little randomness in the measurement, and we're really looking at the signal. A few other things here. This device up here is a small telescope. It looks at the stars. So it can look out and has a computer that will recognize the star patterns and therefore tell the spacecraft how it's pointed, what attitude it's in space. A few of these other things are sun sensors. So if the spacecraft ever resets, the computer resets, it will allow the spacecraft to figure out where the sun is so that the solar panels on the sun to protect the battery while it's waiting for further instructions from the ground. This is one of our antennas to communicate with the Earth. The telescope for the instrument is down here. This is actually, we are so sensitive to water that occasionally, and early in the mission, the first several weeks, we run the instrument quite warm. And what little bit of water is trapped in all of the blankets and all the materials, adhesives, all of that water is slowly evaporating. And so this is a path to get it out to space so it won't create frost on our hardware when it goes cold.
We have time for one more question. We're over here in the back.
Hi, I'm Karen Allen. I was just wondering, how do you keep the satellite safe when it's in orbit? How do you keep it from bumping into other satellites and just general space junk? And what do you do if it does get hit?
So we actually, one of the first things that happens after launch is within about 2 hours, the ULA folks, the people here who are launching the rocket, will give us the injection orbit. So the spacecraft's still warming up. Its GPS system's not running. We don't know where it is until they tell us. At that moment, there's another group at NASA that will take that orbit and project it out several days and tell us if there's anything that's likely to be in our way. If it is, we stop the normal process of booting up the spacecraft and divert to another path to allow us to get the thrusters running as soon as possible so that we can move the satellite. From that point on, every time we update the orbit and get a more refined orbit, it goes back to this group at NASA that is tracking all of the space junk, and they will let us know if there is a risk of a collision. And if so, we'll look at how likely it is, what's going on, how big the particle is, and make a decision on whether we need to move our spacecraft to avoid it. Yeah, you can't see them, they're on the back side here, but there are small thrusters. In fact, that's how we have to merge with the Constellation after checkout in the next couple of weeks. So we have a small amount of ability to reposition the spacecraft. And in fact, the question earlier about how long it would last, it's the fuel to do those sorts of maneuvers that's our limiting life. And we expect we have enough fuel for probably about 12 years if things go smoothly.
Thank you, Randy. Thank you, Pavani. Appreciate it. So you've learned a big overview picture. We've learned about the launch vehicle, and we've learned about the spacecraft. Now we're going to learn a little more about the science. Let me introduce Anne-Marie Eldering, who is the Deputy Project Scientist for OCO-2.
Good morning. Hi, everybody. So you guys as excited as I am? I'm almost out of control. I'm serious. We're going to get this thing up into space. Everything we've been working for years and years and years is finally going to start happening, and we're just so jazzed. I started my day at the science team meeting this morning. We've got 70 folks who are in town to work with us. These are people from US, France, Japan, all over the globe, and they do the science with the data. So this is their last chance to hear the story, prepare for the data, and just get pumped. And I have to tell you, in that room, it was electric this morning. These are a group of those folks were there in 2009 when things didn't work so well. So the expectations are super high, and they're super excited, and it's just, I can't wait to get this thing off to space. So I heard that you talked with Dr. Ken Jux and heard about NASA things. You got Ralph Basilio, Pav, Randy. So they left me to clean up the crumbs. So what do you want to know a little bit about the global carbon cycle, why we're doing this crazy thing anyway? Yeah? All right. Well, let's see what we got. Pull up my first graphic. Here we go, the global carbon cycle. So this is just a little simplified way to show you about how carbon dioxide is moving around, and then I'll tell you a little bit more about why there's something interesting that we don't know yet. So you can see on the top we've got the atmosphere. That's the part of the world we're going to measure. When we burn all our fuel and our gas and our coal, that's where the carbon dioxide goes. But it doesn't just sit there all alone, right? It interacts with other parts of the system. So we've got the oceans over there on the side, and the oceans can actually absorb and dissolve carbon dioxide. And Dave Chris has a great analogy. He talks about when he opens his beer at the end of the day and he puts it on the counter, and you know it's kind of bubbly and fizzy. And if he forgets about it and the thing warms up, it gets all flat. And that's the carbon dioxide that doesn't like to be in the warm stuff, but it likes to be in cold stuff. So the oceans of the Earth, both because of the volume of them and because of the temperatures, will dissolve the carbon dioxide and release it. And you can see some numbers there. There's something like 330 gigatons. That's the number we think of. Gigatons of carbon dioxide that move in and move out of that ocean every year. But they're also about the same size, right? So it's a balanced system. Same thing, you see the trees over here. Remember back when we were kids in grade school, our teachers would tell them about photosynthesis and trees growing. And so when that photosynthesis happens and the trees grow, they actually take carbon dioxide out of the atmosphere and use it to build themselves, to build the leaves and the stems and the roots. And then when they fall down in the fall and they degrade, they put that carbon dioxide back up. So again, you see kind of a balance. You see, what is it, 440 gigatons of carbon going up, 450 coming down. So these things are in balance. But the little one in the bottom, that's you and me and the whole wide world that's burning stuff, digging up the coal, burning it. We put the fossil fuel CO2 up in the atmosphere, but there's no balance to that coming out. So we are changing the overall concentration in this system, and that's part of the big driver of climate change. So that's your global carbon cycle, and I can put those numbers up there, but that's kind of for the integrated globe. We have 100 measurements or so of the atmosphere. We've got a small set of measurements of the ocean, and we use that to say on average what's happening around the globe. And if we look at the next graphic, I'll tell you about one of the other things that's bizarre. Okay, so this is just showing you over time we've made these measurements, and we can see in the red, you kind of looks like a sawtooth, and that's the seasons. That's the leaves taking up carbon dioxide in the summer and then releasing it in the winter. So it goes down in the summer and up in the winter, down and up and down and up. But it's also going to higher and higher concentrations. So back when I was born, concentrations were about 320 parts per million. So you took 1 million molecules of the atmosphere, 320 were carbon dioxide. When we do that these days, we're looking at 400. So think of that. We went from 320 to 400. So we're really increasing the concentrations. So we're increasing concentrations, but we know it's moving around between the land and the atmosphere and the ocean. And let's see the next slide. Okay, and one of the mysteries, this is okay, mystery number one. I told you we're burning carbon dioxide, that's driving the increase in concentrations, but if I look at what I find in the atmosphere every year, it's not always the same. Some years what I add in there almost all stays, and some years what I add in barely stays. So the atmosphere doesn't do the same thing every single year. It kind of has different behavior, and we don't know exactly why. So that's one of the mysteries we want to figure out. And the other mystery, which I don't have a good map for, but I can tell you with words, is that if you said okay, you know the forests are taking up carbon dioxide, but which forest? Can you think of some of the big forests around the globe? You've got the Amazon is massive, right? These rainforests, trees, the jungle, a huge amount of carbon gets stored in those trees. But then if you go to North America and Canada, we have huge forests over big swaths of land. They also have a large amount of carbon. The northern reaches of Russia and Asia, again, huge forests. So which one of those forests is taking it up? And that's what we don't exactly know. And the fact that it's a little different from year to year, it might be maybe the Amazon's really active one year and then less so another year. Maybe North America is really active one year and less. So the part of the puzzle we don't have the answer to is which parts of the ocean, which parts of the forest, and how are they going to behave in the future? Can they always be taking up all this carbon dioxide? Or if this thing goes up twice as high as it is, will the lands and oceans kind of have some limit to what they can do for us, or will they always go up and up? So that's kind of questions we want to answer, and the OCO-2 data is going to help us do that. And really, that's all I want to say in this kind of lecture format. So why don't you bring up some questions you have, or tell me what I didn't tell you, and we can help you get excited about our OCO-2 mission and be ready to get your hands on some of the new info we send out.
We'll start at the back.
Hi, thanks so much for talking to us today about the science. It's really interesting stuff. Randy Pollock was talking to us about how you can measure about 1 ppm CO2 in the atmosphere. So I take that as that's the instrument's resolution, which is very impressive, by the way. So my question is, A, what's your detection limit? What's the smallest amount of CO2 you can measure? And B, is that, combined with your spatial resolution, good enough to be able to measure something like, say, low-level volcanic emissions?
Wow, that's a pretty detailed question. All right, let's see what we can do. So 1 part per million, that is the aim for our sensitivity. And Randy remembers that well because he had to build the darn instrument that was going to do it. So we're aiming at measuring to 1 part per million out of that 400, or about 0.3%. And all the information we have to date from other data sets we've worked with, from the characterization of the instrument and how little noise we have on those detectors, suggests that we should be able to meet those requirements. And it's basically, you know, the level of light that you see gets impacted by these molecules, and so we have to be able to see these very small light level changes, and then also not get confused by other things like the clouds that are in the atmosphere, or perhaps the aerosols and pollution and so on. But we feel like we've got good information that suggests we'll meet the 1 part per million from the data that we collect. And will it be enough to see volcanic emissions? One of the guys on our team just loves volcanoes, and he's always out there telling us about them, telling us about his field measurements, showing us on the maps. And he's been trying to find out when we're going to pass by a volcano. And I think he's convinced that a couple of the big ones you maybe will see. The problem with volcanoes is they also put a lot of junk usually, right? You have volcanic ash, you got water vapor, sulfuric acid. So those things might get in the way, but perhaps we'll catch a plume, or if it erupts in just the right way, we might see it. So I think it's an opportunistic thing, and people will be troving through the data to see if they can do it.
Hi. I'd like to kind of repeat. I have 2 questions, but first of all, if you could talk to us a little bit, kind of like Pavani did, about how you as a woman got involved and how your experience has been. And then also, one thing that Stephanie, I don't know where she went, but Stephanie went, that she likes to say that JPL's missions are unmanned, but the people aren't, and that they carry, the rockets carry your hopes and dreams. So just talk a little bit about your team and kind of like what's your biggest hope that you accomplish with this science?
Wow, okay. These are great questions. You guys are a little more relaxed and asking real things, so this is fun. Yeah, so being a woman in science is an interesting experience. I always was kind of interested in math and science. I loved that stuff when I was a kid. I never knew anyone who was a professional mathematician, so I thought, well, that's probably not something real people do. But my dad was an engineer, and a society of women engineers used to run these programs. If you were interested in engineering, you find out more and understand what's mechanical, what's civil, what's electrical, etc. So I did chemical engineering as an undergrad. I went to Cooper Union. Anyone heard of Cooper Union? Holy cow, yes. Okay, so Cooper Union, tiny, tiny school in New York City, architecture, engineering. Very few people know about it. I went down there and I saw my future unveiling in New Jersey, and I thought, oh, maybe not. In the power, the pharmaceutical plants, the refineries, et cetera, that's where chemical engineers work. So I came to LA, and you wouldn't believe in 1988 when you landed at Caltech in Pasadena and you looked towards the mountains, you saw nothing because there was smog and junk and it was so polluted. So I studied the smog of LA as a PhD, and it was really, really interesting stuff. And what was cool was environmental engineering in my graduate work, 50% of that class was female. So I noticed that electrical engineering didn't have that many women. Chemical engineering, environmental engineering was actually pretty balanced. And I found in my career at JPL, we actually have engineers that pretty much reflect the graduation rates. We have good numbers, and the coolest thing about JPL is if you can get the job done, the job is yours. Nobody cares about, have you been here 10 years or 20 years or what? Nobody cares, or, your background's chemical engineering and now you're working on climate. It's just about getting the job done, and that makes for like an awesome, awesome workplace. Not everything I've ever done was that experience, but JPL has been that experience.
Hi, Matt Campbell at CBS Los Angeles. Given the increase in carbon concentration numbers over the past 50 years, OCO-2 obviously has the potential to predict some fairly alarming temperatures for our future. How much temperature change are humans capable of adjusting to?
Okay, so that is a good question, Matt. How much temperature change are we capable of adjusting to? And as you know, with everything, it's a question of priorities. If we decided we were going to burn all our fossil fuel and have these massive temperature increases, we better be willing to spend a whole bunch of money to make our infrastructure safe, to make sure we can grow the food we need, to make sure the water's available. So, in my mind, for the good of all the people on the planet, the sooner we can cut down on the concentrations, the better off we're going to be. So I'd like to see this information help us understand these natural cycles, make better predictions of the future, and then keep on putting pressure on the global community to make good decisions about cutting down on fossil fuel use as soon as we possibly can.
Thanks. Let's take one from social media real quick over here.
Okay, from the real DJ Flux on Twitter, he asks, is there a data description language that will self-describe the data from OCO-2 or other NASA Earth-observing satellites?
All right, somebody who's ready to actually put their hands on our data. So yeah, we've actually, with NASA, all the data that we provide to the public through our data distribution is in something called HDF, or a hierarchical data format. So it actually has descriptions of the data that are embedded in the file. So if you get a file, you should be able to read it all out. So the HDF and HDF5 right now is the key to unlocking the data.
Hi. Could you talk a little bit about the fluorescence of vegetation that I saw in one of the other broadcasts? And then could you also maybe talk about what are you going to be looking for in terms of other serendipitous stuff that's going to come out of the data stream?
Okay, so the first question was about the solar-induced fluorescence and then other discoveries we think we might find in our data. Okay, so solar-induced fluorescence, has anybody told you about that yet this morning? No. Okay, so I mentioned that when plants photosynthesize, they absorb carbon dioxide. And actually in the photosynthesis process, they do something else. They have heat and energy they have to get rid of, so they actually send a little bit of light back out. And one of the good analogies is if you've ever been in a museum that has minerals, sometimes there's a place where you turn off the regular lights and you shine a UV and you can see this light coming out of the rocks. Same sort of thing, it's fluorescing or emitting. And a couple of folks, one of our team members, Christian, and then Joanna out at Goddard, realized that we have wavelengths that see that light. So they've developed a technique, and this is showing a map of what we expect to see from OCO-2, of basically a measurement of light that leaves are giving off when they photosynthesize. So this is important because it gives you another little lever, another way to look at what plants are doing and what they're doing in the carbon cycle. So if you wanted to just look at that, you might actually design things a little bit different, but we'll actually have a pretty useful piece of information out of here. And other discoveries we might have, that's always hard to predict. You know, we do this sampling, we don't map the whole world, so there's going to be places we never look at, but maybe in some of the places we look at, we'll, you know, find out there's hot spots we hadn't thought about. We'll get to maybe quantify something about how much LA emits relative to the background. People started doing that with the GOSAT data, but we'll get some more information on that. But it's hard to imagine what the science community might end up doing. Plus, we're in that A train. There's other pollution measurements, there's other water vapor clouds, etc. Someone's going to stir that stuff together and tell me something I hadn't thought about, probably about emissions from humans and the CO2 as well as the carbon monoxide and some of the other chemicals. So who knows? Come back in a year, we'll have some new answers. Hey.
Hi, Christina Walsh from Los Angeles with Organizing for Action. I'm thrilled to hear this exciting news about what we're going to learn about carbon. What with the carbon pollution standards that have just been published, and there's a lot of political pushback on that, what do you see as a way to validate this data to the naysayers in Congress and throughout the world? How can that be done, especially with this time lag between now and when we see confirmed data?
Right. So it's always interesting when we try to think about the experiment we're running and the politics of the year and what's going on with carbon dioxide in our government. And so we're first and foremost a science experiment, and remember this was pitched 14 years ago. And the science question is still not answered, so we're still really focused on the science question, but you can't ignore the context of other stuff going on. And I ran some calculations recently, and I took a map of where there's 16,000 big power plants around the globe. But actually, because we see the total column, we only see like the really big ones. Probably 500 or 600 have enough emissions that any remote sensing thing like ours would see it. But then because of where we fly around and what we bump into, we'll actually only cross the path of a small set of the power plants. So just like you asked what we might discover, somebody's going to look at the volcano, somebody's going to look at the power plants, but only a few of them will ever pop up. If the wind's blowing right and the clouds aren't there, we might actually see a trace of the plume passing by. But in terms of sort of convincing the policymakers of how important this stuff is, I feel like our mission isn't going to be the right kind of data to sell them on anything they don't know already. I think we're much more about the implications of those emissions. And if that's where their question is, that's where we're going to have new info to really convince them about stuff. Yeah.
We have one over there.
Yeah, hi, thank you.
Hey.
Ryan Malady, thank you so much for being here and everything you do. I believe I kind of raised my hand before you answered the last question, but yeah, it's basically a lot of the questions I'm getting from Twitter and everywhere else is, can you speculate as to the kind of data that you're going to get and how that will affect global policy when it comes to carbon dioxide and emissions and the human and the kind of effect that, the discussion of the human role in climate change that will have. So if you've answered it already, I mean, maybe some more speculation.
Well, I'll try to say it in a succinct way. When we discuss this amongst ourselves, and of course we do, we talk about the fact that we don't understand how the land masses and the oceans are taking up the carbon dioxide. And if you think about the conversation in the international level right now, we want to try to come up with this scheme where countries can say, this is my carbon emission rate, this is the carbon dioxide I'm taking up. And for example, if I don't cut down my forest, you should recognize that and not count that as a carbon release. And so when people are trying to think about those policies, if we understood better how forests behave, they could do a better job with that kind of analysis. So I think in the big picture, the more we can understand how the natural parts of the system play their role, how long they're going to take up half that carbon dioxide, and how forests are behaving at a more detailed level, that can be helpful to the folks who are trying to really figure this out on the international planning level of things.
Excellent. Thank you very much.
Yeah.
Thank you, Anne-Marie Eldering. Thank you.
Thanks, John. Thanks, everybody.
Okay, for those in the room, I think we still, our speakers are going to stick around and answer any additional questions you may have. For those at home, just a quick programming note that at 2:56 a.m. Tomorrow morning, is the OCO-2 launch. You can watch live on NASA television at www.nasa.gov/NASA television. You can also follow us on social media on @NASA, @IamOCO2. Thank you for joining us, and go OCO2. Thanks.